Hi, we are Team 1 and we have chosen magnetic levitating system as our project for the feedback controls class. And this is the outline. We first go through building a proper support structure and then designing the levitation process and then the mathematical functions. We also had to figure out the distance sensors and then the solenoid drivers and then the controllers, and then a discussion on whatever we have done. So basically the goal of our project is to create a working model of a magnetic levitating system which levitates an object. But previously we considered another model of a repulsive magnetic levitation system where our object is hovering over a solenoid. But we had to drop that idea because of some financial constraints and also some time constraints. So the main parts which we have used is LM741 as an operational amplifier and Y3144 as a Hall sensor, and we used a MOSFET and a pulse width modulation element. So we built our own solenoid and we used a 24 gauge wire which is of 67.66 meters, and we wrapped it around an iron core with around 800 turns, and then we used a 12 volt battery to get 12 volts out of it. So that's how we tested it with around 2 amperes of current. And then based on this formula for magnetic force, you can see that it depends on the number of turns of the solenoid. So if you have more number of turns, you can get more magnetic force out of it. So that's why we used this part.
This is Matthew speaking, and the part of the project that I was most in charge of was designing the body of the levitator as well as building it. So the biggest concern was obviously stability, so my first thought was just to go with metal and wood, which are pretty easy to work with. The metal bars and everything are galvanized steel, so as to not mess with the magnetic fields. This down here is just some brackets and a pin I covered with electrical tape to attach the Hall sensor to. The solenoid was probably the most difficult part to attach just because parts didn't fit exactly how we wanted to, but eventually we worked it out, and all in all we also taped the circuits to the base of it, and the issue was definitely not that our base was not stable, so this worked well, and that's all for the design.
Okay, this is Hanning speaking. I'm charging the theory of the system. Now, for the linearization, we use 2 different blocks to compute the magnetic force. One is for the displacement between the levitated object and the solenoid. Another is the current of the solenoid. And for the block diagram of the process and the sensor, notice that the controller gives the current, and this will generate the magnetic force, but this force has the negative direction of the levitated object movement, so we need to subtract this in the whole feedback control loop.
So this is the design of the solenoid driver which we have used.
Okay, for the design of the controller, first we derived the transfer function of the open loops, and then to get the closed loop transfer function, and then using the characteristic equation to find the exact Kp and Kd parameters. So when we use the PD controller, we assume that it has two parameters, Kp and Kd, and to make the characteristic equations stable, we need two poles in the left side of the complex plane. So we can obtain the range of the Kp and the range of the Kd. This slide shows the range of the Kp, and the next slide tell us how to compute the Kd, and then we choose some values in this range to do our practical system.
We used TL494 as the PWM generator, which gave us an advantage of having two op-amps integrated inside, and which was actually one of them which was actually used for the PD controller circuit to be made, which gave us the advantage of not having a digital part like the Arduino. We didn't have to use that. It was only the PWM generator, the IC-TL494, that was enough for that. And also we used two 10K potentiometers for adjusting the values of the Kp and the Kd. This is the schematic of the levitator, which has been talked about in the later slides, which was not at that time when the video was taken. It is not visible. So this is what we were referring to. This is the upside down view on the left hand side and the front view on the right of our total system. This was the initial one that we did.
Okay, this was one lucky shot we had, and we had to take a photo.
But that was it was for very few seconds, so a very unstable one, you can see.
Hi, my name is Ronaldo Manuel.
Hi, this is Joshua.
And my main task was to put the circuit together. It's basically separated into four main circuits. Off of this schematic, it's all kind of color coordinated with the breadboards. It's back here. So the blue one is the Hall sensors. We started out with 2 Hall sensors, and that didn't quite work out. But we actually kept it on there in case we wanted to use the inverting or non-inverting, depending on the positive or negative input for our transfer function. So the white is actually our PD controller. We used a 494 instead of having to code a Arduino, and actually I thought that was actually a lot easier to use. And then this black circuit right here has the MOSFET and the diodes solenoid. I guess.
So next is first we started off with an IR sensor put on the two sides, but what went wrong with the IR sensor was the range of it. So we had to anyway change the sensor. That's why we decided on the Hall sensor. Now first we used two Hall sensors, one at the bottom and one at the top of the solenoid. But then that was interfering with the magnetic field of the solenoid, so we switched to one Hall sensor and placed that at the bottom. So it was quite far off from the solenoid over here, and there was no interference between the two. Then and also this is very quite sturdy. And also we have this KPKV circuit over here on this one with two potentiometers with which we actually changed the KPKV values. We got a rough idea of the KPKVs from the theoretical section, which we have already mentioned earlier. So we could, in the previous video, you could have seen that we could almost levitate the object, but it was not stable because we could switch the poles from the right half planes to the left half ones. But since there was something which went wrong inside the circuit because of the drop of the current, this object could not be levitated for a longer time. That's what we thought went wrong with our circuit. And also maybe because of the potentiometers, which was not quite of the range that we expected to work for. So this is it, our levitator project. Thank you.
Thank you.
So this is what our project was, and also maybe because the MOSFET that we used, the NTE2394, we are assuming that it burnt out because of a high voltage. So that might be another reason for which it didn't work well. And in this slide we have actually attached the reference data sheets of all the four major components of our circuits for just for reference. So here we are completing our project. Thank you.